Okay, so here we have distorted banded because, again, it was these flat layers and then it got pushed together while it was still partially melted, so then they get all kind of wavy. An example of metamorphism. Toast. What do I mean by that? So my point here is this. Let's say I have, first of all, I like me some toast. Right? I like toast. I wouldn't call myself a toast aficionado, but I enjoy me some toast. Now, I have a toaster oven. Okay? Not a regular toaster where you push the thing down. Those are good, but I have a toaster oven, so that's like a little window there. So you put the bread in, you turn on the heat. And this is how it generally works. You turn the heat on, or you turn it on, it starts, the elements light up, it gets warm, and then put the bread's in there, and it becomes warmed bread. I leave it in there, and then it becomes more warmed bread. And then you start seeing a little bit of the brown forming on there, a little bit toasted, and it's like, I don't know, maybe it's bread that's a little bit toasted, and then it gets a little more brown, and then we're getting, it's a little more toasted bread, and then it gets like kind of brown solid on both sides, like, oh, now it's toast, or there's no definitive time when at one moment it stops being bread and starts being toast. Okay, it's kind of this gradual thing. And then you have, so it's toasting. Oh, it's nice and toasted. It's toasted more. Now it's kind of dark toast. Now it's getting really dark. Now it's like black. And now it's really black. And now it's probably more like burnt toast. I'm going to throw it out. Again, there's no real sort of moment where it officially stops being toast and starts being dark toast. And then it stops being dark toast and starts being burnt toast. It's this gradual thing. And that's what metamorphic rocks are. So, you take something like slate. Slate starts out the parent rock as shale, and then it will gradually sort of, it becomes more metamorphosed, it kind of becomes slate, and then slate more metamorphosed will become, there'll be more changes that occur, and the mineral crystals will change, they get larger, the clay is converting to mica, and then it becomes phyllite, and then it becomes schist. So in that whole range of all these metamorphic rocks, again, it's sort of, you have these rocks that are kind of in between. Is it phyllite or slate? It's kind of in between. Just know that. That's my toast example. The key thing is the high heat and pressure will cause a change, metamorphosis, some minerals change into another minerals. And the main ones we're talking about is like clay of shale will actually convert into mica. Mica is under these conditions, is a mineral that many minerals will change into mica in metamorphic rocks. Therefore, metamorphic rocks tend to have a high concentration of mica. And that gives them oftentimes a very shiny, silvery look. If you remember mica, that thin, flexible and thin sheets is often said, the flaky, really cool, almost looks like plastic sometimes. Minerals is biotite and muscovite. And so metamorphic rocks have a high concentration of mica. That's one way we can tell them from other rocks. Now, the key word is high concentration. It can't just be, it has some mica in it. A lot of rocks have some mica, 10%, 15%, 20%. For it to really be clear that it's a metamorphic rock, it has to have a high concentration, 50%, 60%, 70%, and you see that by it being really silvery and shiny. Now, unfortunately, that is something that never really comes through well in pictures at all. Never really comes through in pictures at all. What's this? Oh, yeah, let's go to this. So, what I did here is on the New York State reference table, what we have is, these are all the foliated metamorphic rocks, so the ones that have layers. As I mentioned them before, slate, phyllite, schist, gneiss. And you go from lower grade metamorphism to higher. So this is lower heat, lower pressure, more. So these are kind of the most changed. And then gneiss being the strongest, most metamorphosed foliated metamorphic rock. So you see in gneiss, maybe in this, I just snapped this picture myself, so it's not great. You see the banding in this piece. Schist often will have like large, large platy mica crystals. You can see them shining off. You really can see them. You can scratch them off and you see the mica crystals very clearly. Phyllite and slate can be a little hard to tell apart. Phyllite tends to, here the mica crystals are microscopic, really kind of hard to see. But in phyllite, they get a little bit larger, and you have much more of a silvery sheen to phyllite. And then just what I have on here too, I have marble, and it's like sort of the crystalline marble. The parent rock is limestone usually, or dolostone. You have quartzite, which is sandstone that's metamorphosed, and sand's usually quartz. Hornfels, God, which is just a boring rock, sorry. It just is. Anthracite coal, which is cool because it is coal that has been metamorphosed. So it's like, we often call it hard coal. It's the best grade coal. You get the most heat from that coal if you were to burn it. It has a really cool, like, silvery shine appearance. Oftentimes when you see it, at first kids can get it confused with obsidian, but it has a different look to it. And from experience, you see it has much more silvery sort of shine to it. It's lower density, but it's cool. Here's a different sort of perspective on it. You see anthracite coal here. The rest of it's not great to see maybe in this picture. Okay. And then this is the chart that we have. Again, slate, phyllite, schist, gneiss. And you can start seeing that all these have mica in them. Mica is a key component. These other minerals are some other minerals common to metamorphic rocks. Quartz, feldspar, amphibole. Garnet is a metamorphic mineral that other minerals change into garnet in these conditions. Hot, lots of pressure, pyroxene. Anthracite coal. These are all non-foliated, so you don't see the layering, so they're often a little hard to tell when they're in your hand. You have a hornfel in your hand, it doesn't look like much. Even marble can be a bit confusing. Quartzite, for a student in high school, hard to tell apart from a lot of other rocks. We're going to skip the airport stuff, and we're getting into, this is a very cool picture of a lava flow. Lava flowing into the ocean at night. This is Hawaii. And other than this being totally cool, I'm showing this here because think about the lava flowing over this rock there, the rock of this cliff. The lava's super hot. It's going to kind of partially melt the rock below it because it's so hot. And that's called contact metamorphism. So that's different than regional metamorphism of where a rock has to be buried deep underground for the high heat. This is directly from lava or magma, and that's going to change the rock. And we often say, geologists use the word cooked, like cooks the rock, or like a baked contact. It will where it contacts the rock, it'll be an area where it's baked, and the crystals can like recrystallize a bit, and you can see it. So do I have a? Yeah. So in this case, what you see here, this rock was existed. This was like probably a crack in that rock, and then there was magma underground, had a lot of pressure, forced its way in the crack and like pushed these rocks apart. So, and this was really hot. So if you were to get up close, I don't have a close-up picture here, you can see the mineral crystals here are going to be probably a little bit larger and like different than over here because it's going to partially melt it along here and along here. And if you look closely, you can see that, which will tell you that this was here and this came second. We often note that this is the symbol on a piece of paper when you draw it. This is the symbol showing contact metamorphism for this igneous intrusion. And it helps us date that this was here, this came second, as opposed to maybe this being here and this came second. So, because this had to be here for this to come through and kind of cook it.